Before we begin our derivation, it is important to review some vector calculus concepts. First, we note that any vector can be decomposed into its Cartesian components. The Cartesian components are the projection that that vector has along three orthogonal axes. For instance, in the picture we can see that the vector p has a projection along the width direction of p sub x, a projection along the height direction of p sub y, and a projection in the depth direction of p sub z. If we add up the components, we result with the vector p. It is usual to define I as a vector of unit length in the x direction, j as a unit vector in the y direction, and k as a unit vector in the z direction. Other useful vector calculus relations include the dot or scalar product of two vectors, which is defined as p dot q equals p sub x, q sub x, plus p sub y times q sub y, plus p sub z times q sub z. That is, you take the x component of p and multiply it by the x component of q, and do likewise for the y and z components of those two vectors. The dot product is equal to the magnitude of p times the magnitude of q times the cosine of the angle made between those two vectors. Note that it obtains a scalar result. It is just a number with no direction. The vector or cross product of any two vectors is defined in a much more complicated way. P cross q is equal to p sub y q sub z minus p sub z q sub y times a unit vector in the x direction I, plus similar constructs for the other two directions. This cross product is also called the vector product because it results in a vector quantity that has both magnitude and direction. Moving now to calculus, recall that the partial derivative of any scalar is defined as follows. The partial derivative of p sub x with respect to x is given by p sub x evaluated at x plus delta x, y, z, and t, minus p sub x evaluated at x, y, z, and t, all divided by delta x in the limit that delta x goes to 0. A useful quantity from vector calculus is the gradient operator, which is equal to the partial derivative with respect to x times a unit vector in the x direction, plus a partial derivative with respect to y times a unit vector in the y direction, plus the partial derivative with respect to z times a unit vector in the z direction. And the divergence of any vector is defined as taking the dot product of this gradient operator with that vector. As you can see from the definition of both the gradient operator and the dot product, the result is given here. It is partial of p sub x with respect to x, plus partial of p sub y with respect to y, plus a partial of p sub z with respect to z. And the curl of a vector is defined as by taking the gradient operator and crossing it, getting the cross product with p. That expression is much more complicated and is shown here. Continuing with the vector calculus review, recall that it is possible to decompose any vector field into its longitudinal and transverse components. The longitudinal component of the vector field is a portion of the vector field that has zero curl, while the transverse component has zero divergence. Since the longitudinal component of the vector field has zero curl, it can be expressed as the gradient operator applied to a scalar field psi. Psi is just a simple function that has a single scalar value at every point in space and time. Applying the gradient operator to psi results in the expression shown here. One can then take the curl of the longitudinal component obtained in this fashion to easily show that the curl does indeed vanish. Here we can see that each term in the expansion involves partial derivatives with their order of operation reversed. For well-behaved functions, this will result in these terms canceling each other out, showing that the longitudinal component obtained in this way indeed does have zero curl. Next, we will use the fact that the divergence of the transverse component is zero to show that the divergence of the vector p is equal to the divergence of its longitudinal portion. This is because the divergence operator of the transverse part is zero, and that leaves us with the divergence of the longitudinal portion. And now, since the longitudinal component of p is equal to the gradient operator applied to psi, when we take the divergence of the longitudinal portion, we are taking the divergence of the gradient of psi. The divergence of the gradient operator is called the Laplacian operator. And what we have arrived at is the fact that the Laplacian operator applied to psi sub p is equal to the divergence of p. I've put red boxes around this result and labeled it as equation 1, as we will use this expression later on in this webinar. As a last step in our review of vector calculus, another result that will be used below will be discussed here. The result is that if we decompose p into its longitudinal and transverse components, and we have the condition where the divergence of p sub l is equal to 0, then we can choose p sub l to be equal to 0 by a proper choice of p sub t. We can see this by first assuming that p sub l is not 0, but rather it is some remaining function r. But since we have the divergence of p sub l equal to 0, this means that the divergence of r is 0, since p sub l is equal to r. And so from this fact, we can form a new transverse component, p prime sub t, which is equal to our old transverse component, p sub t, plus the new vector r. And we can form a new longitudinal component, p prime sub l, which is equal to our old longitudinal component, p sub l, minus that vector r. This will still leave us with the gradient operator applied to the new transverse component of 0, since each term is 0, but it will also leave us with the fact that the longitudinal component is now 0. Therefore, we can choose our components such that p sub l is equal to 0 if we have the condition that the gradient of p sub l is 0. As an example for a non-zero value of r, we can consider the case where r is some constant. Since the partial derivatives of a constant are 0, it is easy to see that a constant will have 0 divergence and 0 curl. If p involves some constant and we wish to form a longitudinal component that is 0, our choice must then be to assign the constant part of p to the transverse component of p when we decompose p. The same holds true for any function r that has 0 divergence.